Hi, I'm Robert Crowe. Welcome back to part 2 of our 3-part series on sharding and parallelism. Let's explore how to scale your Flax NNX models using JAX's powerful distributed computing capabilities, specifically its SPMD paradigm. If you're coming from PyTorch and have started using JAX and Flax NNX, you know that modern models often outgrow single accelerators. We'll discuss JAX's approach to parallelism and how NNX integrates with it seamlessly. This episode focuses on the main workflow, how to integrate JAX's sharding primitives with Flax NNX, with a special focus on the critical sharded initialization pattern. So let's get started. In our last episode, we laid the foundation for scaling our models. We explored why distributed training is essential and covered the core strategies like data and model parallelism. We then introduced the fundamental JAX primitives, the mesh to define our hardware topology, the partition spec to describe how our tensors should be laid out, and JAX.JIT, which triggers the SPMD compilation. Now, we're going to build on that foundation and connect it directly to Flax NNX. Okay, let's quickly recap Flax NNX. Unlike pure JAX, NNX modules are stateful Python objects, much like PyTorch modules. They hold their parameters and other state directly as attributes, usually initialized eagerly. A crucial feature for us today is that these state variables can store metadata. We'll use this to attach our sharding hints. However, this statefulness traditionally clashes with JAX's functional nature. The big news is that in NNX version 0.11 and after, is that NNX modules are now native JAX PyTrees. This closes a major conceptual gap that we had in earlier versions. While the module object itself is still a mutable Python object, it can now be understood directly by JAX transformations, and NNX provides the bridge to handle this correctly. So how do we reconcile NNX's mutable objects with JAX's functional transformations? Well, NNX provides two ways. First, the functional API. You explicitly split your module into its static definition and its dynamic state, which is a JAX-compatible PyTree. You pass this state through JAX.JIT or JAX.grad to get the result, and then merge or update the original module. Alternatively, NNX provides its own wrappers, like NNX.JIT and NNX.grad. These handle the split merge process under the hood, giving you a more seamless experience, although potentially with some slight overhead compared to the manual functional API. Now let's connect NNX and SPMD. The Flax NNX SPMD module lets us attach those partition spec hints directly to our parameters as metadata when we define the module. We can use helper functions like NNX.withMetadata around your initializer, passing a sharding argument with the partition spec tuple. Sometimes you can even pass the sharding argument directly to NNX.param. This stores a partition spec tuple in a .sharding attribute on the variable state. Crucially, this doesn't shard the parameter yet. It's just metadata, a hint for later. Here's what those two options look like in code. First, the preferred method using NNX.withMetadata. Second, annotating the variable directly, in this case, and NNX.param. Okay, this is the core workflow and addresses a common pitfall. If you just instantiate a very large NNX model, even with sharding annotations, JAX might try to create all parameters on a single default device first, leading to an or out-of-memory error. The solution is to perform the initialization and the application of sharding inside a JIT-compiled function, We'll use nnx.jit for convenience. Inside this function, the first steps are instantiate the module. The parameters are created, but likely still on device 0. And then extract its functional state PyTree using nnx.state. Continuing inside our JITted initialization function, next we use nnx.spmd.getPartitionSpec. This utility function walks through the state PyTree we just extracted and pulls out all the .sharding metadata we added earlier, creating a parallel PyTree of partition-spec objects. Then comes the crucial step. We use JAX.lax.withSharding constraint, passing in the original state and the partition specs we just extracted. This tells the JAX compiler, when you produce the final result for this state, make sure it conforms to these sharding specifications. Here's what that last part looks like in code. We use nnx.spmd.getPartitionSpec to pull out all the .sharding metadata we added earlier, creating a parallel PyTree of partition spec objects. Then we use JAX.lax.withSharding constraint, passing in the original state and the partition specs we just extracted. The final step inside the JITted function is to use nnx.update. This takes the sharded state, which JAX and XLA will ensure is correctly distributed upon execution, and merges it back into our original mutable model object. The function then returns this model. The key is to call this entire createSharded model function while inside a withMesh block, or a mesh context. This provides the context JAX needs to actually fulfill the sharding constraints across the specified devices. The result, sharded model, now holds parameters physically distributed across the mesh, avoiding the single device or out of memory. So, inside the JITted function, we get our sharded state and merge it back into the model with nnx.update. Then finally, we execute that JITted function in a withMesh context. For better abstraction, instead of hard-coding data or model inside your module definitions, you can use logical access names like batch, sequence, or embed, or hidden. You then define a separate mapping called sharding rules that translates these logical names to your actual physical mesh access names. You can provide these rules when initializing variables or attach them later. This makes your model code more portable and easier to adapt to different hardware setups or sharding strategies, as you only need to change the rules and not the model definition itself. Here's an example of using sharding rules to map logical access names to physical mesh axes. We define sharding rules as a tuple of pairs where each pair maps a logical name like batch or hidden to a physical mesh axis like data or model. For example, batch data means that anything annotated with batch will be sharded along the data axis of the mesh. You then use these logical names in your NNX module definition when initializing parameters, providing the sharding rules through nnx.withMetadata. And this approach allows you to define your model independently of the specific hardware layout, making your code more flexible and adaptable to different sharding strategies. You can learn more about JAX and the entire JAX AI stack with these coding exercises, quick reference docs, and slides. To watch the whole Learning JAX series, check out our playlist on YouTube. There's a growing community on Discord for JAX, and here's an invite link. And here are links to the docs for JAX, Flax, and the JAX AI stack. We've just walked through the most critical part of this entire process: how to safely initialize a massive sharded NNX model. By annotating our parameters with sharding metadata and wrapping the instantiation inside a JITted function with the wish sharding constraint, we've solved the single device or out of memory problem, and now have a model with its parameters physically distributed across our accelerator mesh. We've sharded our model, but what's next? How do we feed it data, run the training step, manage checkpoints, and see all of this in action with a real-world example? Coming up in our next episode, we'll put it all together. We'll build the distributed training loop, discuss efficient data loading with Grain and sharded checkpointing with Orbax, and then walk through a complete practical example of sharding a GPT-2 style transformer block from start to finish. See you there, and don't forget to hit like and subscribe.